Hellenistic science and technology. When it comes to science and technology in the Hellenistic era, we can basically divide the achievements into four main areas: medicine, astronomy, geometry, and technology. Let's talk about medicine first. The main thing to know about medicine is that we have another one of the fathers of a discipline. We have Hippocrates, this is him right here, hello, who is the father of medicine. How did this come about? Well, it's because Hippocrates worked at Epidaurus, which was the Greek shrine to Asclepius. It's up at the top of the Peloponnesus. And for many, many generations, ever since at least the Archaic Age, people would go to Epidaurus to be healed by the god Asclepius. This is the god Asclepius right here. You might recognize him because he's got the caduceus. He's got the caduceus right here, the caduceus, which you see on ambulances today. It's a symbol of health, just like Asclepius was the god of health. That's the thing. Epidaurus worked there. Now, how did things work at Epidaurus, the shrine of Asclepius? Well, people who were sick would overnight in the temple. They would actually spend the night there with the priests of Asclepius. You can even see Asclepius back here, and they would spend the night there, and that would, according to the stories, they would get healed. And then when they were healed, they would then offer thanks to the god by leaving a votive offering. A votive offering is when you donate a representation of the part of you that was healed and put it in the temple to show other people that you were healed. So for instance, in this one, you can see very clearly, it says, Asclepio kai eugeia tuke eucharisterion, which means thanksgiving to Asclepius and to something fortune. I don't know what eugeia means, but something fortune right there. So you can even see, that's just one, that's a leg, so obviously someone see the leg, but here you see all kinds of body parts that people would go to the temple to be healed from. You actually see this even today in Latin American countries and in Italy, where at Catholic shrines, people leave hearts to represent that they've been saved or healed from some kind of emotional distress, or they leave crutches and helmets to show that they've been healed from some kind of physical distress, leaving votive offerings in the churches or the shrines. So basically, that's how it worked at the temple of Asclepius at Epidaurus. Hippocrates worked there, and since he worked there, he was able to observe sick people, and he decided to set out a systematic study of how to heal people. His basic observation was quite simple. His basic observation was that every disease gets worse until you reach the point of crisis, and at that point, the patient either gets better or dies. Because of this, Asclepius also advised physicians only take the cases that they know they could heal. We talked about this before when we did the Law Code of Hammurabi. The liability for people dying goes upon the doctor back then. There's really no protections for the doctor. So Hippocrates told people only accept the cases you know you can heal. But one of the things he's probably most famous for is he wrote the Hippocratic Oath. Here it is right here. This is the Hippocratic Oath. Basically, the formula to swear when you become a doctor. Its basic content is, I will do no harm. That's basically the idea of the Hippocratic Oath. And it used to be an oath taken by all doctors before they began their practice. It's been modified somewhat. Some doctors don't take it at all anymore. Other doctors take a modified form. You can see that right here. And one of the main reasons for the modification is times have changed. For example, in the Hippocratic Oath, it says explicitly, I will give no pessary for abortion. So basically it says that helping someone abort their child is not something that Hippocrates is going to do because that goes against the principle of do no harm. Today, obviously, many doctors can't bring themselves to agree with that, so we've changed the oath, or we just dropped it altogether. But that's the Hippocratic Oath. It goes back to Hippocrates, the father of medicine. Now let's move on to astronomy. There are really great men in astronomy at this time. One of the greatest is Aristarchus of Samos. Why is he such a big deal? Because he argued for heliocentrism. Now, that's a fancy word, but all it means is the sun in the center. That might not seem like a big deal to you, but for most of intellectual history, most people believed in geocentrism because of Hipparchus. Hipparchus disagreed with Aristarchus of Samos and said, no, I think the Earth is in the center of the universe. And that's not going to be that's going to be the main theory up until Galileo and Copernicus and Kepler in the 16th century AD. So in a way, Aristarchus of Samos is pretty exceptional in that he already way back in the Hellenistic era was arguing for a universe with the sun in the center. But unfortunately, he wasn't believed, and eventually Hipparchus's theory dominated, where the Earth is in the center. Now, before you call Hipparchus stupid, his math was actually better in the sense that both of them were basically trying to explain the same thing. Both were trying to account for the retrograde motion of the planets. When you look at the stars in the heavens, the stars actually behave pretty well. They're actually pretty easy to predict. What's crazy is the planets. The planets go back and forth in the sky. So both Aristarchus and Hipparchus were trying to show you why do the planets seem to go back and forth. In Aristarchus's heliocentric model, which was perfect circles, you can show you why. Watch Mars right here. This is Mars. This is actually the real Mars, but this is what it looks like to the observer. And watch what happens from the point of view of Earth as this model goes. So watch the animation here. So as the Earth revolves, Mars goes a little bit slower, and so it looks like Mars is kind of going up and down as the... let me play that one more time. It looks like Mars kind of goes up and down as Earth is going. But here's the thing. It was great, but... Hipparchus did the same thing. He posited that the Earth was in the center, and that that each planet not only revolves around the Earth, but also goes in its own little epicycle, like a circle on a circle. And if you do that, Mars also goes back and forth. And so both accounted for it well. But in the end, Hipparchus, followed by Ptolemy, had a model that was a lot easier to predict for many, many years. As a matter of fact, it wasn't until the 17th century with the data from Kepler, the 16th century with the data from Kepler, that people realized that his model is just a little bit off. And once they realized the model was a little bit off, that things were about a minute of a degree off from where they should be in the Ptolemaic calculation, they realized they had to go back to the heliocentric theory. But nevertheless, both of these guys are geniuses because they're trying to plot the stars. Even more amazing, and also my personal favorite when it comes to astronomy, is Eratosthenes of Cyrene. Now, why was Eratosthenes of Cyrene such a big deal? Really for two reasons. For one, he drew a map of the entire known world based on the new knowledge of the Hellenistic era. As you all know, Alexander conquered a lot, so it was time to update the maps. And so he made this map right here that you see. And even though to you it might look simple, you can start to see some things. You can see Italy right here. You can see Arabia. You can see even, I believe over here is Sri Lanka. You're starting to see some of the things that we all know on this map. The other interesting thing about this map, there's two more interesting things about it. One is you got lines of longitude and latitude, which shows that he knows that the Earth is round. It's important to emphasize that every educated person at this time knew that the Earth was round. No one thought it was flat, and that will remain true up until forever, basically. No one's ever really, this knowledge will not be lost. Everybody knows it was flat. So this idea that Columbus was trying to prove the world is round and everybody else thought it was flat is simply false. The other thing you notice about this map, though, is a little bit of a mistake. You all know when you study geography today that we say there are 7 continents and we divide Europe and Asia into 2 of those continents. And then you look at a globe or a map and you're like, why is Europe and Asia 2 continents? It should be one. It's one huge landmass. And you're right, it should be one continent. But the reason we separate it goes back to this map, because look right here at the Caspian Sea. Today we know the Caspian Sea closes off and you still have Russia, which is a huge massive land connecting Europe and Asia right here. And so there's no reason today to say it's 2 continents. But back then, as you see, they didn't know that. They thought the Caspian Sea opened out into the ocean. And so when you actually look at this map, when you step back and look at it, of course there's 3 continents. Here's Europe, here's Asia, and here's Africa, which back then they're calling Libya. So the division of Europe and Asia actually goes back to Eratosthenes. Now, even though that seems like a bit of a mistake, you got to give him credit for the map of the time. But even more credit goes for his other main achievement, which is amazing. He also accurately measured the circumference of the Earth, all from within Egypt. He never left Egypt, and he was able to measure the circumference of the Earth. How far off was he? He was only off by 450 miles, which sounds like a lot but when you drive it, but compared to the circumference of the Earth, it's not a big deal. He did a great job. Now, how did he do this? Well, for those who care, let's get a diagram right here. Basically, he knew that on a certain day every year, there was the sun was directly over a well in Aswan, which back then was called Syene. And you could tell because you could see the reflection in the water. So if you draw an imaginary line from the sun through the well, perpendicular to the bottom of the well, to the center of the Earth, you've got one angle, or one side of the angle that you need. Now, he had a friend over in Alexandria, which is 5,000 stadia away. He knew that was 5,000 stadia away, so he had his friend in Alexandria do him a favor. basically at his friend. Notice the shadow of the obelisk, and that meant that the sun was shining in a parallel line from the top of the obelisk to the edge of the shadow. So then if you extend that imaginary line like this, you get two parallel lines, one here and one here. Now, then if you take the obelisk and presume it straight up, you've got a transversal. So now that you've got the transversal, all you need to do now is measure, first of all, the angle of the obelisk from its shadow. So basically this angle right here, if we call that angle x, then here's the other thing. Since it's crossing a line, from geometry you can know that that's equivalent to this angle. Now we'll call that angle y. Now, but since you have a transversal across two parallel lines, you know that that angle y is equivalent to this angle, which they call here alpha. So this angle alpha you now know, because if you know this angle, you know this angle. If you know this angle, then you know this angle. If you know this angle, you know this angle. That means that he knows the angle now, and he can basically measure it. What he got was basically 1/50th of a circle. That's how much he got, 1/50th of a circle. Now you have the two data you need. You have this distance right here, 5,000 stadia. You have a 1/50th of a circle. Do the math, you get 25,000 stadia, which is basically correct, only off by 450 miles. Now, speaking of geometry, we also have during this time the father of geometry, the great Euclid of Alexandria. Some of you may know him if you're doing geometry here at Providence Academy. Euclid of Alexandria is considered the father of geometry. He's the author of the 13 books of the Elements. That's the book he wrote. And he's basically the origin of Euclidean geometry. If you're doing geometry where you have to prove a certain conclusion from certain givens, and you have to prove it exactly and logically, you're doing Euclidean geometry, and he is the father of that, so you can blame him. But he's a great man in the sense that he got his geometry rules even today. Now, you might not think of the past as a time where technology was huge, but in the Hellenistic era it actually was. People were experimenting a lot with various things, and it's pretty amazing what they were able to create at this time. Particularly four people. We'll see the next one, the fourth one on the next slide. But there were three great technology people of this time. They called them the machine men. They were Philo of Byzantium, Ctesibius of Alexandria, and especially Hero of Alexandria. As a matter of fact, he was called the Machine Man. What did they do? They made pretty amazing things. Using steam power or using wind-up mechanisms, they were able to make almost what you would call robots. For example, Philo of Byzantium was able to make this robot right here. It's basically a robot that you turn a switch on its back, and once you turn the switch on its back, that switch tells you how many parts water you want to your wine. Because remember, the Greeks drank their wine mixed with water. So you do this setting on the back, and then you put the cup in the hand. As soon as you put the cup in the hand, it automatically pours the correct amounts of water and wine. This is a copy right here, but it was pretty amazing. You can see how someone is figuring out how it works right here, that you had this. They made a lot of little interesting things like this. Ctesibius of Alexandria made a pretty accurate water clock. Here's a representation right here. As you can see, it's rather complex. It's not just one simple water clock. But Hero was the best. Hero made all kinds of things. For example, Hero of Alexandria made the world's first steam engine. Now, this might not look much like a steam engine to you, but it does basically operate on the power of steam. Basically, you light a fire down here, and that heats up the water. The water goes up into these pipes right here, and then sprays out of these two, I guess you would call them siphons, and then the whole thing spins like that, and you can basically spin this wheel by the power of steam. It'll take a while before they figure out how to harness that power for actual useful production, but they've already got steam engines back then. He also made this wind-powered organ. When you play the organ, you need someone to pump air, but not in the case of Hero's organ. All you need is a little bit of wind, and that would spin this windmill right here, and then you pump it up and down, and you would have air to play the organ. Another amazing thing he made was this this self-opening temple. Pretty amazing. What would happen is a priest would be ready to offer a sacrifice. Just give me a second, let me back it up. A priest would offer a sacrifice right here. As it was burning, it would heat up the water. The water would then fill up this weight as it transferred into this siphon right here, and then that would open the doors. So you'd be like, ooh, Zeus is opening the doors. The priests offer the sacrifice and the doors opened. It was kind of spooky. Another thing he did was he made this little TV show. This is all a little puppet show, but it's all automatic. You wind it up, and for 20 minutes, it tells you a story of the return of one of the heroes from the Trojan War. And it included thunder and, by rolling marbles, making noise and things like that. It included all kinds of things. He even made this little machine, this little interesting trinket where when you pick up a cup of water and pour it into this jar, wine comes out of this jar into your other cup. So it's like it's turning water into wine with this little machine. You can actually see how it works right here. So you get the idea. They're actually making pretty amazing things. All this gets lost, by the way, because the Romans just don't care. As a matter of fact, the Romans find some of these people very disturbing to them, particularly Archimedes of Syracuse. Now, I'll get back to his relationship with the Romans in a second, but first let me describe this great Archimedes, one of the greatest scientists of this time. For one thing, Archimedes discovered the buoyancy principle to determine whether the tyrant of Syracuse's crown was made of gold or lead covered with gold. Basically, the tyrant of Syracuse received a crown that he commissioned a metalsmith to make. And the king had the suspicion that the crown was actually made of lead covered with gold and not really made of gold. So he said to Archimedes, figure out if this crown is lead or gold, but you're not allowed to destroy it to find out. So Archimedes was trying to figure out, how do I solve this problem? And he couldn't figure out how to solve it, but he started to take a bath. And as he took the bath, he noticed that he displaced the water with his body, and he displaced the more density something had, the more water it displaced. And he suddenly realized what he needed to do. And he was so excited, he ran out immediately from his bathtub and shouted, "Eureka!" through the streets of Syracuse. Then he used that principle to figure out that the crown was indeed lead. He also did a lot of work with simple machines. For example, levers. He's famous for his quote, "If you give me a place to stand, I can move the entire earth." Now, it's not literally true because there is no place to stand, but his point was how a lever can increase power or increase force, make force a lot easier by increasing distance. Or a screw. A screw counts as a simple machine. It's just a revolved inclined plane. And one of his main inventions with the screw was the Archimedean screw, a way to pump water. All you do is you turn a crank that would theoretically be up here, and that makes the water follow up this inclined plane, and then you have water. This works well in places that don't have electricity, for example, and it's still used today in places that are just building infrastructure when they need water immediately. This is one way to get water, this Archimedean screw. But he also built siege weapons, especially when the Romans were going to attack Syracuse later. He made a lot of siege weapons to attack the Romans. The Romans became very much afraid of him. For example, he made this thing that the Romans called the claw. No one knows exactly what it did, but here's an artist's conception. A claw that just came out, grabbed your ship, shook it until everybody fell out. It's kind of spooky. One other thing that he's said to have done is use mirrors to burn the Roman ships. Use concave mirrors to burn the Roman ships, as you see right here. They were so mad about this that when they took the city of Syracuse, they were afraid of the wizard of Syracuse, and pretty much immediately they killed Archimedes when they finally did take the city. So he died at the hands of the Romans, who were basically afraid of this man who could make such terrible war machines. Finally, in technology, one of the greatest devices ever that we found from this time is the antikythera device, or the antikythera mechanism. We have no idea who made it. It was discovered off the coast of the island of Antikythera in the early 1900s. Why is it a big deal? Well, basically, it's possibly the world's oldest computer. Now, when you hear computer, you might think electronics, but this is basically a mechanical computer. Here are the pieces right here. You can see it right here that we found. But putting them together, you basically can figure out that it looked basically like this. So putting all the pieces together, it was a complex geared mechanism that looked basically like this when it was used. Now, what was it used for? Well, basically, here's another artist's conception, by the way, what it probably really looked like. It's quite beautiful in many ways. Basically, the way it worked was you would turn a knob on the side to represent the passage of time. And as you turned that knob, the device displayed the phases of the moon, the course of the sun and the planets, and the signs of the zodiac, and it even predicted solar and lunar eclipses. You can see that right here on this video. See, as it comes forward, here's this right here is the moon representation. Here's the knob that you turn. As you turn the knob, the moon goes through its phases. I think this is this is indicating the signs of the zodiac that the sun is in. And then if you turn around on the back, you see two other dials that represent the eclipses of the sun and the moon. So it was a pretty amazing machine. You know, if you could basically plug in any date and find all the information about the heavenly bodies in that time. It was very complex. I mean, take a look at it right here. Here's a representation of the gears that were operating in it. Just give me 1 second. Right here, you get a representation of all the gears that were involved. Hold on, just move this text aside. It's amazing because it is basically the system of gears does mimic quite exactly the solar system as known in that model. Although in this particular model showing the heliocentric model, it followed the geocentric model. But it's amazing that they were able to basically reproduce the solar system in a machine. That shows you how great the technology was at the time. It's a wonderful time, and thank you for listening to a presentation on the science and technology of the Hellenistic era.